we have now done MO diagrams for every element in the first row of the periodic table. So it's time for us to move to the second row. And where we're going to start in this video is with pretty much going across the entire second row and only dealing with the homonuclear diatomics. So each element will be paired with another atom that is identical to it in the next video. Or maybe 2 videos from now, in a later video, we will do heteronuclear diatomics and point out the differences between the two. So let's just start at the beginning, and let's start with dilithium, so Li2. Now, I'm going to start by drawing the MO correlation diagram, and let's give me a little more space on this one. So I've got an energy scale. I'll have a column with lithium atomic orbitals. In the middle, I'll have my dilithium molecular orbitals. And then the right-hand column will be my lithium atomic orbitals, since this is a homonuclear diatomic. So in the second row, lithium has the 2s and technically the 2p. I'm going to leave the 2p off of this picture, but we're in that row, so they technically exist. They're just empty, so we're not going to need them, and I want to explicitly go through drawing some of those pictures with the p orbitals as soon as we get past this, because they're going to be necessary as soon as we get to the second half of this row. So, like I said, I'm going to do just the s orbitals. So I've got a 1s here, and hopefully I'm leaving myself enough space, a 2s, which means my other lithium atom has the exact same AOs at the exact same energies. Now, my 1s, it's going to behave exactly like we saw before. So the 1s is going to overlap and give me a sigma 1s. And a sigma star 1s. They should be spaced evenly. I'm just going to do my best here. 1s, that is what that says. And then my 2s, when I combine those with each other, they're going to do the exact same thing. So I'll get a bonding combination. It'll be a sigma 2s because I combined two 2s orbitals. And I'll get an anti-bonding combination, sigma star 2s. So you can see why it becomes important to put these connecting lines. So I'm going to connect the 2s to these molecular orbitals to show that that's what's contributing. Connect my 1s for the same reason. Okay. So that's all my AOs, it's all my MOs. I've got my energy label and my columns labeled. So let's fill in the electrons. Lithium has 3 electrons total, right? Its electron configuration is 1s2, 2s1. So let's fill those in. And then I have 2, 4, 6 electrons total for the molecule. So if I put these into my MOs, 1, 2, 3, 4, 5, 6, and that's it. I'm out of electrons. So I can calculate a bond order. I'm going to stop color coding these, but you are always welcome to do so in your notes to help you keep track of things. So I lied. I'm going to color code these. Bonding electrons, sigma 1s, sigma 2s. Anti-bonding, sigma star 1s, sigma star 2s. There we go. And number of electrons in bonding MOs, I have 4. And number of electrons in anti-bonding MOs, I have 2. So I had 2 anti-bonding MOs, but only one of them had electrons in it, and it had 2. So 1/2 of 4 minus 2 is 1. So dilithium exists. It has a single bond. But what you will find, and let's do green here. All of this, we've spent a lot of time talking about how important valence electrons are and kind of ignoring everything happening in the core. So we're in the second period now. So the 1s orbitals are core orbitals, and the electrons in them are core electrons. So when we fill in these MO diagrams, our core orbitals, and they will always be full. Which means when we do bonding minus anti-bonding, they're always going to cancel each other out. So we'll say, and not contribute to the bonding order. So we just leave them off. So you will see, and it's not incorrect to draw the core set, but once we start having the s and the p orbitals in our MO diagram, it's just going to be a little bit prohibitively tall. If we also include the core, plus the core doesn't tell us the information that we need about the bonding order, because it always cancels out if you have all of the bonding and all of the anti-bonding in the core filled up. So if we did the bond order using the valence electrons only, which means my sigma 2s, which has 2 electrons in it, and my sigma star 2s, which has 0 electrons in it, my bond order is 1/2 of 2 minus 0, and I get 1. I get the same answer, so it's perfectly okay to leave the core off of our diagrams going forward. Now, we'll just tack this on at the bottom. The pictures, the way that we're drawing 2s orbitals, they don't look any different from 1s orbitals. So sigma 2s, well, it's going to look like I took 2s orbitals and brought them up next to each other. And a sigma star 2s, well, it's going to look like I took 2s orbitals and brought them up next to each other, but out of phase. Okay, so this is what everything will look like with the s orbitals. I'm not going to do whatever's next, beryllium, but if you want to practice, you are welcome to do Be2 to show what it looks like. I do want to start looking at p orbitals. So what about p orbitals? Just like with the s orbitals, and just like I described in the intro, we're only going to combine the ones that are of the exact same type. So the pictures that we get will depend on how they're oriented in space. So we need an axis system. We very conveniently have an axis system that we are used to using. So each element has px, py, pz, and we're just overlapping the orbitals of the same type. So let's just summarize. Each element has, right, this is my py, px, and pz. So my combinations, if I do a px plus a px, I'm putting in 2 orbitals. I better get 2 molecular orbitals out. It will be just like we did for the s. I'll have a combination in phase and a combination out of phase. And my x orbitals, my px orbitals actually, plus px, they point at each other. So it's a p orbital, but that's head-on overlap. It's a sigma interaction. So the MOs that I get from combining, let me make sure I spell interaction right. The MOs that I get from combining the px orbitals will be sigma MOs. All right, so let's do my in-phase combination first. And then to the right of that, we'll do my out-of-phase combination. All right, make sure these are shaded properly. All right, so just a reminder, the part that we're looking at, right, one atom is here on the left. We can imagine, maybe even imagine like we're pushing it closer to the one it's connected to. And that one is on the right, and we're pushing it closer to the one that it's connected to. So the lobes that matter, being in phase or out of phase, are just the ones that are pointed at each other. And it is solely a result of them being the px. This is the way that px is oriented with our axis system. Okay. So if I combine my in-phase orbitals, it looks kind of weird. Like this lobe on the left, nothing has changed about it. These two lobes in the middle overlap, give me kind of a, I don't know, a giant super lobe. And then this lobe in the right is totally unchanged. So all of this is shaded because it started out shaded, and I've got constructive interference here. This is my sigma P, and let's even explicitly say, since we're starting in the second row, my sigma 2p bonding orbital. This is the type of picture I would like you to draw. You need to be very clear with the outer lobes because they came from pure p orbitals. They should not look like they came from the hybrid orbitals that we were drawing with valence bond theory. All right, when we do this out of phase, right, the interaction is between the shaded lobe and the unshaded lobe. That's a destructive interference. It's going to give me a node in the middle, and my orbital on this side shaded this way, my orbital on the right shaded this way. So this is a sigma star 2p anti-bonding MO. Okay, so that's px. I'm going to do py and pz all kind of side by side. So hopefully my pictures won't get too small here. So py plus py, just based on the way that my py orbitals are pointed, right? Py would be pointed in this up and down direction. Those, when they come together, it's going to be sideways overlap. So I'm going to get a pi interaction out of py plus py. So let me also set up another set of py's because I'll end up with an in-phase and an out-of-phase combination. And then let's just put a dividing line here. And the pz plus pz. So my pz points out and back, and then I'll have another combination out and back, out and back. These pictures are going to get just a little bit harder to draw, so do the best that you can to draw them as MOs and show the perspective. So on the py side, I'll have a bonding combination. So that's, say, both of the top lobes shaded. When they come together, the two shaded parts will interact, so it'll be constructive, and the two unshaded parts will interact, so that will be constructive. And I'll have an anti-bonding, which means the top lobes are oppositely shaded and the bottom lobes are oppositely shaded. So the one on the left, this gives me a pi 2p bonding MO. And what I end up with is this kind of blob on the top that's from those two shaded lobes adding together. And then I've got this like blob on the bottom that's from the two unshaded lobes adding together. The next combo, pi star 2p anti-bonding, which I'm going to abbreviate because I'm kind of running out of space. It's destructive interference all the way across. So I'll have a node and then a p orbital on this side with the top shaded, p orbital on this side with the bottom shaded. All right. PZs, if both of the front lobes are shaded, when I bring these together, the front lobes will overlap with each other. So both shaded means constructive. The back lobes will interact with each other. Both unshaded means constructive. So this is also sideways overlap, also 2p. So this is another pi 2p bonding. And the front lobes will look like this kind of shaded blob, and then the back lobes will look like an unshaded blob. So it looks exactly like my pi 2p bonding from the py. It's just rotated in space because of how the orbitals were oriented. All right, last bit, I need an anti-bonding combination. So the front lobes are opposite shades and the back lobes are opposite. Pi star 2p anti-bonding. And this results in a node, and then I'll have a p orbital on the left shaded in the front, p orbital on the right shaded in the back. Now, just like every other situation, if your shading was opposite my shading, it's totally fine. What really matters is same shades give constructive interference, opposite shades give destructive, and if you have all constructive, you have bonding. If you have destructive, you have the anti-bonding. So you notice these all really look a lot like each other. They're just kind of pointed in different directions. And so this is going to be really important in our MO diagram pictures, because this pi 2p bonding and this pi 2p bonding, get them connected, these have the same energy. It's the same types of orbitals overlapping in the same way. They're just, one's pointed on the y-axis, the other's pointed on the z-axis. We call these degenerate. And they will have the same energy in our MO diagram. So it's going to get just a little more complicated, but it should be familiar because it's going to look like when we were drawing, say, electron configurations for atoms, all of the p orbitals had the same energy. Now we're going to have some MOs that have the same energy. And, right, my anti-bonding combination, they look exactly the same but pointed in different directions. These also have the same energy, but they're anti-bonding, so it's just higher energy than the bonding combinations. Okay, so I am going to give you pictures of what these MO diagrams look like. Part of the reason I'm going to give you pictures is because there are two different versions of the picture that we're going to have to deal with. I am going to ask you to memorize the pictures. I am not going to ask you to come up with them on your own. So you'll have some rules for figuring out which one to use when. Okay. So as we go across the periodic table, right, it's boron. So if we're talking about homonuclear diatomics, we're talking about B2, and then C2, N2, and then O2, F2, Ne2. So this is basically just my P block. The MO diagrams for these have a great big dividing line right here in the middle, which is hopefully going to help you figure out which one goes when. So B2, C2, N2, the first half of the period, these all use something called a second order MO diagram. And O2, F2, Ne2, in the second half, these all use a first order diagram. It's a very small difference between the two diagrams, which I'm about to draw right below this, but you do need to use the proper diagram in order to get the correct answer, because it can make a big difference in your bond order depending on how many electrons your molecule has. All right, now we're going to do this for valence only. So let's do another big dividing line just so they don't overlap too much. So that's going to divide the second order from the first order. And then for my second order diagram, let's get an energy label here. Hopefully this is big enough. Put my E at the top just in case. So I'm just going to use like X for my, I don't want to use X. Let's use A because it's not an element and it doesn't mean anything. X sometimes explicitly means a halogen. So we're not really dealing with the halogens, especially on this side. I mean, we do have one halogen on the other side. So my A atomic orbitals, my A2 molecular orbitals, and my A atomic orbitals. I do realize that I could just get a picture of this and put it in here for you, but I want you to draw these out and not just copy paste a picture or screenshot a picture. So I'm going to hand draw them here. All right, just dealing with the valence orbitals, this A atomic orbitals, it has two P's, the set of three, all at the same energy, and it has a 2s. All right, I'm trying to pre-plan and make sure I have enough room here. And you won't see me moving this, but I'm going to get my 2p a little bit lower in energy so I have some space. So these are homonuclear diatomics. So the atomic orbitals for the other A atom, my 2p's will be at the same energy, and my 2s will be at the same energy. The 2s orbitals come together to make a sigma 2s and a sigma star 2s. And the 2p orbitals, we've drawn all the pictures, but we've not yet thought about what that might look like on an energy scale. Now, the things that you can count on, the bonding will always be lower than the anti-bonding. And after that, what we do in this class doesn't really prepare you to make other decisions. So I'm just going to tell you that for everything in this first half of the diagram, the lowest energy is the set of pi 2p. So one line represents the pi 2p from the py. The other line represents the pi 2p from the pz. Then there's the sigma 2p, which came from our px. And then in the anti-bonding, the pi star 2p are next, right? So it's a pi star from the py and a pi star from the pz. That's why there are two lines. And then the sigma star 2p. Hugely important to put in these connecting lines, especially now, so the 2p's contribute to all of these, and then my 2s contributes to the sigmas and the sigma star 2s. Wowzer. Okay, this is a second order MO correlation diagram. This is the orderings of the orbitals that you should use when you are doing something like B2, C2, or N2. All right, a first order diagram Let's get my energy scale on here. I'm gonna write my E in there really tiny. I planned my space very poorly, but that's all right. I'm still gonna have my A atomic orbitals, my A2 molecular orbitals, my A atomic orbitals. A is gonna have a 2s, so this A is gonna have a 2s, and 2p, and 2p. There's nothing different about how the s orbitals interact, so I will have a sigma 2s and a sigma star 2s. And I'm just gonna get my color switched and go ahead and connect these, right, with the connecting dots. It's when I look at how the p orbitals overlap that there's one very small difference, and it is just that the lowest energy is now the sigma 2p, and then the pi 2p is above it. The antibonding doesn't change, so the pi star 2p is lowest, and then the sigma star 2p. So let me get these connecting lines in here. Okay, that's it. So let's do a little more highlight dividing so that we can tell the difference between these. So make a big, strong highlight line to separate the two types of diagrams. But then I want to do kind of a highlight box here across both of them to show you. Let's get a really light color. I don't know, orange will be okay. So it's the P combinations, the bonding MOs that show a difference in their placement. Let's see if that will snap in nicely. So it seems maybe less intuitive, but right, the first half of the period does a second order diagram. A second order diagram means that the pi 2p, which has two levels that are degenerate, is the lowest energy. The second half has a first order diagram, and in a first order diagram, the singular sigma 2p level is the lowest energy. Okay, so this is a lot. Here's what I want to tell you as a wrap up for these pictures. These energy orderings were determined by calculations. So you would not necessarily predict these. We had a computer calculate them for us. Were determined by calculations. You will need to know these diagrams. And you will need to know when to apply them. So I may just ask you to draw an MO correlation diagram for C2, and you'll have to know which one to pick, and you'll have to put it together. And I think that's it. I think that's the main point that I wanted to get there. So you need to know them. You need to be able to draw them. Hopefully the tricks and the first half, second order, two levels at the lowest energy will kind of help you remember what goes with what. And I want to check this just against one molecule, since this video is getting super long. Let's check against a molecule we know. Let's check it against O2. So we can finally get an idea about where those two unpaired electrons might come in, since we said it was a failure of valence bond theory. So let's draw the MO correlation diagram for O2 and then compare it to the Lewis structure. So the Lewis structure part's pretty easy. We could throw that together in a second. And my MO correlation diagram. So O2, oxygen is in the second half of the first period. It uses a first order MO correlation diagram. So one column will be my oxygen atomic orbitals. The middle will be my O2 molecular orbitals. And then the right-hand column will be my oxygen atomic orbitals. Okay. The valence electrons for oxygen are in 2s and 2p. So I'll have 2s and a 2s here at the same energy. Honestly, I'm going to go ahead and fill in my MOs so that my space planning works out a little bit. Get a sigma 2s combo and a sigma star 2s combo. Then I will have the 2p orbitals in the atomic columns, also 2p here. And first order, the lowest energy combination is my sigma 2p, then pi 2p, and there are two of them, right? One from the combo of the py's and the other from the combo of the pz's. And then my anti-bonding, oh, hi Muggsy. Muggsy wants to say hi. It's the pi star 2p and the sigma star 2p. Get my connecting lines. Connect these MOs from the p orbitals to my p atomic orbitals and the ones from my s to the ones from s. Okay. So oxygen has 6 electrons per atom, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I have 12 electrons to put in my molecular orbitals. Starting at the bottom, 1, 2, 3, 4, 5, 6. Ooh, I have 2 orbitals at the same energy. I have to follow Hund's rules. So I'm at 6, 7, 8, 9, 10. Well, that one's filled. I have 2 left, 11, 12. In this pi star 2p, I have 2 unpaired electrons. So this is exactly where my 2 unpaired electrons show up in my MO diagram that I can't account for in my Lewis structure. If I do a bond order calculation, let's highlight these. I can't remember what colors I was using, so hopefully this is right. Orange for bonding, pink for anti-bonding. My bond order is going to be 1/2 of 2, 4, 6, 8 in bonding MOs and 2, 4 in anti-bonding MOs. 8 minus 4 is 4, divided by 2 is 2. So I get a double bond. So my MO picture agrees with my Lewis picture in that I get a double bond. The 2 unpaired electrons match the experimental data. I just don't have a way to nicely show them in a Lewis model. It just isn't made to account for that. So as a practice, which I'm not going to go through because this video is super long, do the MO correlation diagram for N2 and see how it compares to the Lewis structure.